Okay, so now we're going to take a look at some of the formulas we're going to use in this course. So this starts the portion of the class where you can have a formula sheet for exams. It's going to contain all of the formulas we'll do in Unit 3, starting with the sum and difference formulas. So now you don't need to worry so much about memorizing these because the formulas we're going to look at are fairly complicated, but you do need to be able to do applications of them. So the sum and difference formulas give us ways to rewrite the cosine, the sine, or the tangent of the sum of two angles or the difference of two angles in terms of trig values of the component angles. In this video, I'm not going to go through the derivation of these formulas. It's something that we can do, but it's also fairly time-consuming. What I think I will do is just write up a written proof and post it to Canvas of one of these. I'll probably do the either sum or difference formula for cosine, and then the other ones kind of follow from our elementary trig identities, that once we know the sum and difference formulas for cosine, we can use the cofunction identities to get them for sine, and then we can take quotients to get the ones for tangents. That's how we would do that in practice. But today we're going to focus on just doing some application problems. So for example, cosine of alpha plus beta, if alpha and beta are two angles, is the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. So for example, if we wanted to find an exact value for the cosine of 75 degrees, 75 degrees doesn't have 30 degrees, 60 degrees, or 45 degrees as a reference angle, so we can't use just the unit circle or quadrants and reference angles to get this cosine value. But what we can do is think about 75 degrees rather, as being 45 degrees plus 30 degrees. Okay, so this would be one way to express 75 degrees as a sum or difference of two angles whose trig values we know. Okay, so now we're thinking about 45 degrees as being our alpha, 30 degrees as being our beta. So now this is going to be, we're going to use the sum formula for cosine. So this is going to be the cosine of our first angle times the cosine of our second angle minus the sine of our first angle times the sine of our second angle. Okay, so here we're just using the formula. This is cosine of 40 degrees times cosine of 30 degrees minus sine of 45 degrees times the sine of 30 degrees. So this is, and remember I like to keep the square roots in the denominator, so I'd write this as 1 over square root of 2. Cosine of 30 degrees is square root of 3 over 2. Sine of 45 degrees is 1 over square root of 2. Sine of 30 degrees is 1/2. Okay, so note that both fractions have a denominator of 2 times the square root of 2. So we can combine them by subtracting the numerators. Our first numerator is the square root of 3. The second is 1. Okay, so we'd end up with the square root of 3 minus 1 over 2 times the square root of 2. Okay, so that's an exact value for the cosine of 75 degrees. Okay, so that's one way that we can use the sum and difference formulas. Just as they're written from left to right, we have an angle that we're trying to find a trig value of. We can write it as a sum or difference of angles whose trig values we know, and then do the evaluation. So there are two different variations on this problem as well. The first is if we want to use the trig identities from right to left. So this is actually an easier problem, even though it doesn't really look like it at first, where we have something that's actually the right-hand side of the trig identity written out, and we just need to simplify it to look like the left-hand side, and then we can do the evaluation. So remember, a trig formula or trig identity is an equality, it's an equation, so the left and right hand sides are always equal. So for example, if we wanted to simplify the sine of pi over 12 times the cosine of 2 pi over 3 plus the cosine of pi over 12 times the sine of 2 pi over 3. Okay, so note that we have two angles here. We have pi over 12, which is kind of like an alpha, and 2 pi over 3, which kind of looks like a beta. So what you don't want to do if you're presented with this sort of problem, of course we could find the sine and cosine of 2 pi over 3. But what we don't want to try to do is find the sine and cosine of pi over 12. That's something that we could do using various formulas, one of which is a difference formula. What we want to do instead is rewrite this as something simpler. So we're going to look at this and note that it takes the form sine alpha cosine beta plus cosine alpha sine beta. So if we just generically replace pi over 12 and 2 pi over 3 with alpha and beta, we're going to have something that looks like this. But that is exactly the sine of alpha plus beta. So that tells us that we can rewrite our original expression as the sine of pi over 12 plus 2 pi over 3. Okay. So now let's simplify that. We need a common denominator. In this case, our common denominator will be 12, so we'll take 2 pi over 3, multiply the top and bottom by 4. That gives us 8 pi over 12. Or we have the sine of 9 pi over 12. And 9 over 12 simplifies to 3 over 4. Okay, so we have the sine of 3 pi over 4. 3 pi over 4 is a second quadrant angle with a reference angle of pi over 4. So the sine is 1 over square root of 2. In other words, this big complicated expression, if we use the sum formula for sine, but now we're going to use it in reverse, we have something that looks like the right-hand side, we're going to make it look like the left-hand side, that's going to simplify to the sine of 3 pi over 4, which is just 1 over square root of 2. And so whenever you have a big complicated expression like this, it usually pays off to look at your formula sheet and say, okay, is this the right-hand side of one of our formulas? Can we make it look like the left-hand side? So we're not always using our formulas from left to right. We sometimes use them from right to left. All right. Now let's take a look at one last problem type. And this is going to be similar to the first example we did in that we're using our formula from left to right. But instead of being given numerical values for our angles, like 30 degrees and 45 degrees, we're going to be given information about our angles that allows us to find the sines and cosines. And I'm going to erase the tangent formulas here just to give myself a little extra space. And you should note that, as will be the case with really all these formulas, if you know the sine and cosine versions, we don't even really need the tangent versions because you can take sine divided by cosine and get the tangent if we were so inclined. Okay, so let's suppose that we have two angles, alpha and beta. So let's suppose that the terminal side of alpha is in quadrant 1. And beta terminates in quadrant 4. And let's further suppose that the sine of alpha is 8 over 17, and the cosine of beta is 3 over the square root of 11. Okay, so we're given one trig value for alpha, one trig value for beta, and we want to find, we'll do the cosine of alpha plus beta. Okay, so this is just a combination of using the formula and then finding the missing trig values by drawing right triangles in the appropriate quadrant. Okay, so we're going to use the fact that, just from our formula, the cosine of alpha plus beta is cosine alpha times cosine beta minus sine alpha times sine beta. Okay, and what do we know? We know right now the sine of alpha is 8 over 17, and we know cosine of beta is 3 over the square root of 11. So we've got to find cosine of alpha and sine of beta. Okay, but we can do that because we have a quadrant and we have a trig value. So let's start with the angle alpha. Alpha terminates in the first quadrant, and its sine is 8 over 17. So here's alpha. We'll draw a first quadrant right triangle. Sine is y over r. So our vertical leg will have length 8, our hypotenuse will have length 17. This is a Pythagorean triple. The x value needs to be 15, because 8 squared plus 15 squared is 17 squared, so this is a slightly bigger but still important Pythagorean triple, 8, 15, 17. If you didn't have this committed to memory, then you could work it out just using arithmetic. 8 squared plus 15 squared is 17 squared. So for this right triangle, the length of our missing side is 15, and therefore the cosine of alpha is 15 over 17. So now let's do the same thing with beta. So now beta terminates in the fourth quadrant. So we know the cosine of beta, we want to find its sine. So there's beta, fourth quadrant. We'll draw a fourth quadrant right triangle. Cosine is 3 over square root of 11, so our x will be 3. Our hypotenuse, our r, will be square root of 11. So now we're going to have 3 squared plus y squared equals square root of 11 squared. Okay, so 9 plus y squared is 11. And therefore y squared is 2. So y is negative the square root of 2. So here we're in the fourth quadrant, where y is going to be negative. And therefore, the sine of beta is negative the square root of 2 over the square root of 11. So we're going to put that in our formula. Okay, so that leaves us with 15 times 3 is 45 over 17 times the square root of 11. We have two minus signs that will cancel, so we're going to be adding 8 times the square root of 2 over 17 times the square root of 11. The nice thing about this sort of problem is that our denominators should always be the same, because they're going to be the products of the hypotenuses for our two triangles. So if you do this sort of problem and you end up with two different denominators, there's a chance you did something wrong. So again, these are the problems where you're given a quadrant and a trig value and you have to draw the right triangles. So now we can just add these and we get 45 plus 8 times the square root of 2 over 17 times the square root of 11. Okay, so those are the three main problem types you'll see when you're doing sum and difference formula problems. In the next video, we'll look at the double angle formulas, which actually come from the sum and difference formulas.